we want to find the solution to this differential equation, f prime, which is the same as dy dx, equals e to the negative x squared. And we want f of 7 to equal 3. So it's an initial value problem. And we just need to integrate, right? Well, what's the integral of e to the negative x squared? Anybody know that integral? No, probably not, because there is no explicitly defined function that is the integral of e to the negative x squared. There are no simple basic functions that you can just take the derivative of and get e to the negative x squared. Seems weird that that's not possible, but it's true. You can't do that. So we could then just say that f of x, and how did we integrate way back when we were doing fundamental theorem of calculus stuff? We said we'd integrate it from some constant to x e to the negative t squared dt, and there should be some constant attached to this too at the end, right? Since this is an indefinite integral and we're trying to find some extra constant attached. Does that seem reasonable from what we were doing before with the fundamental theorem of calculus? So like if I took the derivative of this from a constant to x, I'd get e to the negative x squared, and I took the derivative of that, that'd go away. So the derivative of this is this, and this seems to be the integral, but we'd like to be able to figure out what constant 1 and constant 2 are. Does that make sense? Is that good or no?
So where it says t, is that supposed to be x?
Well, I mean, so remember back when we were doing the fundamental theorem of calculus, we had these were originally in t's just so that when we took the derivative, we could plug the x's in for those other variables. These could be x's here if you wanted them to be, but generally we write them as a different variable. We call it a dummy variable.
Okay.
Gotcha. It should be something other than x, but it's not a huge deal if you choose to use x. So the question is, we haven't incorporated this f of 7 equals 3 into it yet. And so that's going to be what allows us to figure out the value of both of these constants. Because if I plug in 7 for x, f of 7, that should be the integral from constant 1 to 7 of e to the negative t squared dt plus constant 2. True or no?
True.
Okay. So, and this should equal what? Should equal 3. So if we want to be able to figure out constant 2, we also need to know what this value is. But it's very difficult to evaluate the integral of something when we don't know the integral of that function. There's only one way that we can be certain what this value is, since we don't know what the integral of e to the negative t squared is. And that would be if constant 1 were equal to what?
Seven.
Sorry, two of you sort of said something at once, and I'm not sure what you said.
I was just going to ask you to repeat, but it's all good.
Oh, I just said, so what does constant 1 need to equal so that we can evaluate that integral?
Would it be 7?
For example, if constant 1 was 0, do you know what the integral from 0 to 7 of e to the negative t squared is? Nope, you don't, right? You don't know what that is. What if constant 1 was 1? Do you know what the integral from 1 to 7 of e to the negative t squared is? Nope, you don't, right? Okay, well, what's the one number that you can plug in there that you do know what that integral is? Think back to the rules for integrals that we talked about.
7, right? So then the answer would be 0?
Yeah, if that was 7, then this integral from 7 to 7 of e to the negative t squared would be 0. right? So if we let constant 1 equal 7 and had the integral from 7 to x of e to the negative t squared dt plus constant 2, what would constant 2 then equal? We have 0 plus constant 2 should equal 3. So constant 2 would be 3. And we could then say that f of x should be equal to the integral from 7, c1, to x of e to the negative t squared dt plus 3. And while this is not a great solution to this problem, it is a solution to this problem. And if we had a calculator at our disposal, which we will on the next couple of problems, we could then figure out what f of 10 was, right? We'd just plug in 10 and let our calculator approximate this integral. Or even without a calculator, we could still approximate this integral, right? We could use a rectangular or trapezoidal approximation to approximate the value of this integral from 7 to anywhere. Does that make sense? Or no? Okay, let's do another one since nobody's answering. We want to now find f of 2 if f prime of x is x to the 4th sine x and f of 3 is 5. So does anybody know the function that is the integral of x to the 4th sine x?
No.
No, probably not. So let's say that f of x is equal to an integral of t to the 4th sine t dt plus some constant. And we're still going to want to go from somewhere to x up here. And what do you think the value for our lower limit should be?
Three?
It'd be 3, because that way when we look for f of 3, we're putting in a 3 for the x, and this whole thing will come out to be 0. So f of 3 is the integral from 3 to 3 of t to the 4th sine t dt plus some constant, and that needs to equal 5. And so what does our constant come out to be? What's the integral from? Yeah,
It's
gonna be
5.
Good, okay. So that tells us that f of x is equal to the integral from 3 to x of t to the 4th sine t dt plus 5. And if we want f of 2, then we'll just use our calculator to approximate the integral from 3 to 2 of t to the 4th sine t dt, and then add 5 to it. And so give you guys a second there to type that into your calculator. When you type it into your calculator, you can just make all the t's x's. But I'll give you a minute to punch that in and let me know what you get. Anybody got an answer there?
Negative 14.98.
Negative 14 somewhere.
98.
Give me 3 decimals on it.
988.
988. Yeah. So on the AP test, you always give at least 3 decimals if you're using a calculator to approximate. And we'll talk more about that another time, but always at least 3 decimals. Everybody agree with that value? Anybody get something different? I have an issue with that.
Nope.
All right, you guys want to try and do this one on your own?
Yeah.
All right, I'll give you a minute or two to work through it and see what you get. Ready, go. All right, so hopefully you said f of x is equal to an integral of 1 over ln t dt plus a constant. And your lower limit should have been 9, and your upper limit should have been x. And since f of 9 is equal to 5, that's 0 plus c, it tells you that your constant is 5. And so f of x in the end ends up being the integral from 9 to x of 1 over ln t dt plus 5. Good or no?
Good.
Wait, does it matter which one you set as your upper and lower limit?
Sorry, say that again.
Does it matter, like how do you know if 9 is your lower limit or your upper limit?
You want to put it as, normally we put it as our lower limit, because that way when we take the derivative, I mean, you have to put it as your lower limit, because when we take the derivative of this, we need to get 1 over ln x. And the only way to take the derivative of the integral to get the original function is from a constant to x.
Okay.
If it was x to a constant, it gives you the opposite of it, because you have to flip the limits and put a negative in front of it.
Okay. Thank you.
Does that make sense?
A bit, yeah.
All right, and so what did we get when we evaluated that?
I got 0.324 approximately.
Other people agree with that?
Yep.
Cool. Perfect. All right, so you're going to have an assignment tonight where you have to do a few of these. They almost every year put 1 or maybe 2 of these into the calculator multiple choice section, usually just 1. But it's easy points if you know how to do it on your calculator. It's real quick and easy. So that's why we practice this. But it's just another type of initial value problem where you don't actually know the integral of the function. All right, so we go back to some where we do know them, but we're going to talk
I have a
about.
question, Mr.
Yeah.
Bachelor.
Yeah.
When it says an f of whatever value equals a number, like in this case for both of those 5, is that generally what c is equal to?
Yeah, in fact, it always will be. So as long as you set it up so that the f of whatever, f of a, is your lower limit, then that will make this your constant.
Okay, thank you.
Now, because we're always going to plug in, then the upper limit will also be 9, and so that cancels all of this out, and you just get 0 plus c equals whatever that other value was. So it'll always be c. Good? Does that make sense?
Yeah, thank you.
All right, so we're now going to transition back to doing ones that we can do completely by hand without a calculator at all, but we're going to do it in terms of position, velocity, and acceleration. So the derivative of position was velocity, right? And the derivative of velocity was acceleration. So if you integrate acceleration, you ought to get velocity, and if you integrate velocity, you ought to get position. True? Does that make sense? From back when we did motion before, derivative of position was velocity,
Yes.
derivative of velocity was acceleration, and then backwards. So let's see if we can then figure out the position of a particle if we know something about its initial position and if we know the velocity function. So that's our goal for right now. How should we start this out?
Integrate the v of t equation.
All right, good. So x of t should be equal to the integral of v of t dt, which ought to be, what's the integral of 2t cubed? Should be 1/2 t to the 4th. And what about the integral of 3t squared? That one should be plus t cubed. Everybody agree with that or no?
Yeah.
And then plus a constant. And so if x of 2 equals 1, say x of 2, which should be 1/2 of 2 to the 4th plus 2 cubed plus c needs to equal 1. Well, half of 2 to the 4th is 8 plus another 8. That's 16 plus c equals 1. So what does c equal?
-15.
Great. All right, so c is -15, and then we'll go plug that in. X of t is equal to 1/2 t to the 4th plus t cubed minus 15, and we want x of 3. And what do we get? That's 81/2 plus 12, which I guess is 105/2. Good or no?
Good.
Good.
All right, let's do another one. I'll have you guys work through this one on your own. So this one, we've got acceleration and we're trying to find velocity. So you'll have to integrate acceleration to get velocity. I'll give you guys just a minute to 2 minutes should be plenty to do this. So you guys all feel like you could do that?
Yeah.
All right, ready, go. All right, so since there was no response, we'll just say v of t is equal to the integral of a of t dt, which is what?
Negative cosine t plus c.
Negative cosine t plus a constant. And we want, or we know that v of pi is equal to 3, so that should be negative cosine pi plus our constant. And what's the cosine of pi? The cosine of pi is -1, right? So a negative -1 gives us 3 equals 1 plus c, or c is 2. So v of t is negative cosine t plus 2. And v of pi over 3 ought to be negative cosine pi over 3 plus 2, or -1/2 plus 2, which is 3/2. Good or no?
Good.
Good.
All right. You guys want to do another one on your own?
Yeah.
All right. So this one is a little bit more difficult. We're starting with an acceleration function, and we want to get a position at 2. So first, we're going to have to find the velocity function and the correct constant for that. And then we'll have to integrate a second time to get the correct position equation, finding the constant using this, and then plug in 2. So this will take you a little bit more time. I'll give you 3 or 4 minutes here for this one. Ready, go. First off, you should have integrated your a of t function. So v of t should be the integral of a of t, which was what? T cubed plus t squared over 2 plus t plus a constant. And v of 2 was 9. So 9 needed to equal 2 cubed plus 2 squared over 2 plus 2 plus c. And what did that constant come out to be?
-3.
I got -3. Yeah.
Yep, -3, good. And so v of t was then now equal to t cubed plus t squared over 2 plus t minus 3. And so we'll integrate that to get x of t. So x of t should be t to the 4th over 4 plus t cubed over 6 plus t squared over 2 minus 3t plus a constant. And then you plugged in 1 to get 6. So we had 6 equals a 4th plus a 6th plus a half minus 3 plus our constant. And what was our constant this time? And we'll call this constant 1, just so that we distinguish from our original constant.
97 over 12.
97 over 12. Sound good to everybody? Other than not liking that number?
Yeah.
All right, cool. So then we will just go back in and say that now x of t, which is now t to the 4th over 4, plus t cubed over 6, plus t squared over 2, minus 3t plus 97 twelfths. And we'll look for x of 2. So x of 2 should be 2 to the 4th, which is what? 16 over 4, so 4 plus 8/6 or 4/3 plus 2 minus 6 plus 97 over 12, which was 97 twelfths plus 4/3 because the 4, 2, and the -6 all cancel. So looks like that came out to be 113 over 12. Good or no?
Good.
Any questions or issues or problems with any of that? No? Everyone's good? All right. Let's see. How much time we got? We still got some time, right? All right. We have a little bit of time then to move into what we're going to finish talking about tomorrow. We may not get as far as I did during 4th grade. But the next thing we're going to start talking about is something called slope fields. And a slope field is just a way for us to basically make a graph of the solution to a differential equation. So as we've already noted today, for example, with, let's see, this one, there are some functions that we don't yet know how to take the integral of, right? Like 1 over ln x, x to the 4th times sine x, or especially e to the -x squared, because there's no good way to take the antiderivative of that. There is, though, a way, using what we call a slope field, to come up with a graph that approximates the solution to that differential equation. And so that's what we're going to make an attempt at doing today. Sound good or no? Okay, great. So how it works is we need to think about what a differential equation is. And a differential equation should just be something that, like we said, represents the derivative of a function. And what is a derivative of a function?
It's like the rate of change of another function.
Sorry, say that again.
The rate of change or the slope of another function.
Right, it's the rate of change or the slope, and the key word there is slope. It's the slope of another function. And So what we're going to do is we're going to take the slopes of our differential, or we're going to take the slopes of our original function using the differential equation of it, because that differential equation should represent the slope of our original function at any point that we are interested in. And so if we can just sketch little tiny pieces of what that slope looks like on little tiny intervals, then we should have a general idea of what the graph of the solution to the differential equation looks like. And so we're going to start off trying to do this with one that we know. We know that if dy dx equals cosine x, what should the solution to that differential equation be?
Y equals sine x.
Sine x plus some constant, right?
Yeah.
So whether it's a sine curve way up here, or a sine curve way down here, or a sine curve going through the origin, the solution to this has to look like a sine curve. And so we're going to show that that's true by sketching out this thing called a slope field. So we will start that off by thinking about what's happening here with this function. Is there an x and a y value in our differential equation that affects both, that affects the derivative, or is it just an x value that affects the derivative? Like the value of the derivative. So like if I said, what's the value of the derivative at the point 0, 7? Is the value of the derivative the same at 0, 7 as it is at 0, 2? Or at 8, 7? Which of those would have the same value for the derivative? If I plug in the point 0, 7 into cosine x, does
It
the
would be
y
the same
value
as,
affect this derivative?
no, it would
No,
be the same
only-
as 0, 2.
Right, only the x value does. So let's see what happens to dy dx if x is 0. What do we get? We get the cosine of 0, which is what's the
One.
cosine of 0? Somebody should be able to tell me what the cosine of 0 is.
It's 1.
Oh, good. All right. It's 1. Wonderful. So the cosine of 0 is 1. And so that's going to tell us that anywhere where x is equal to 0, we're going to just sketch a little line that has a slope of about 1. Right? So that's what we've done. Sketched a bunch of little lines where x is 0 that have a slope of 1. What about when x is pi over 2? Let's call this next value over here pi over 2. What do we get?
0.
Should be 0, right? So that'd be a bunch of little lines with a slope of 0, or horizontal little lines. And what about if x was pi?
-1.
Be -1, so we get something like these. And what if x was 3 pi over 2? Be back to 0. And to 2 pi, be back to
1.
good. All right, and what about negative pi over 2? That'd be 0. And negative pi would be -1. Negative 3 pi over 2 would be 0. And negative 2 pi would be 1. And if you think about putting a point somewhere on here, let's put a point right here at the origin, and we follow the basic trajectory of these lines. As I'm at 0, I should have a slope of 1, but between 0 and pi over 2, I should narrow out to get to a slope of 0. And then from pi over 2 to pi, I should get down to about a slope of negative 1. And between there and 3 pi over 2, I should get down to about a slope of 0 again, and then back up to a slope of about 1. And the same thing should be happening over here. And what does it look like?
Cosine curve.
Hopefully it looks like a sine curve, right?
Yeah.
Because it should look like the solution to our differential equation, which is y equals sine x. And a sine curve, right, it has its midpoint there, right there at the origin. It goes up to a max at pi over 2 and down to a min at 3 pi over 2, or at negative pi over 2. So this should look exactly like a sine curve, not like a cosine curve, although obviously sine and cosine curves are related and very similar. Specifically, this one looks just like a sine curve, which is the solution to the differential equation. Does that make sense? Or no?
Yeah.
Cool. All right. Let's see. We still got a couple minutes. All right. So here's what I'd like you guys to do then. I'd like you to first off, well, together, let's think about, do the x and the y values of a point matter for this one, or is it just the x values? Again.
Just the x, right?
Looks like it's just the x values again. So I want you to figure out at x equals 0, 1, and 2, and 3 maybe, and over to negative 3, what the slopes should each be. So x is, we'll say, 0, 1, 2, 3, and let's go negative 1, negative 2. And I want you to tell me what is dy dx for each of those. So take just, I don't know, a minute and plug in each of those values in here to figure out what dy dx is. Ready to go. All right, so what do we get? For 0, we should have got
1.
okay, for 1, we should have got
1.
okay, for 2,
Root 3.
okay, for 3,
Root 7.
negative 1,
Root 3.
and negative 2.
Root 7.
All right. So we would note then that anywhere where x is 0, we'd have a slope of 1. Anywhere where x was 1, we'd also have a slope of 1. Anywhere where x was 2 would be root 3, which is a little more than that. So it's getting a little steeper. Anywhere where x was 3, it's even steeper. And the larger we got, if I'd asked you to find 4 or 5, we'd find that it just keeps getting steeper and steeper. And same over here. If we go to negative 1, it's a little steeper. And over here, it's even more steep. And so we would find that the solution, let's say the solution that goes through the point 0, 0, would look steep, flatten out some, and then get steep again. So even though we may not be able to exactly find the antiderivative of that function, there are ways to do it, but even though we may not be able to yet, we can still sketch a graph that shows an approximation of what the curve looks like if it goes through a certain point. And we just sort of follow the trajectories of those lines until we get a nice smooth looking curve. Make sense or no?
Yeah, that makes sense.
All right, so tomorrow we're gonna sort of go beyond this whole idea of slope fields with these single variables of just x, and we're going to introduce x and y into our differential equations and see if we can sketch the solution to a differential equation that has multiple variables. But for today, that is going to be it. Any questions on what we've done today? All right, that's it.